Okay, hi everyone. Thanks to the organizers for the invitation. It's a pleasure to be here. We're all the way here from Ontario, Canada. And so our presentation is entitled 3DP Ceramic Screens, and we'll go over how we've been leveraging toolpath design to functionally grade material properties across kind of the breadth of our body of research. So as Nadja mentioned, it's worth noting that we're part of a research team at the University of Waterloo School of Architecture, led by Associate Professor David Correa, who started the research program in 2017, and we've been with the team since 2019. And so this is kind of a brief overview of the presentation. So we're going to go through 3 projects. We'll first go through grading light, which operates kind of at a mesoscale of toolpath development. Secondly, we'll look at Hive, which looks at leveraging toolpath design on sort of a macro scale in a 3DP masonry system. And then lastly, we'll just go over some of our teaching as part of the University of Waterloo, as well as the Architectural Association Visiting School. So it's kind of worth noting that kind of the scope of the research really focuses on utilizing functionally graded additive manufacturing at different scales to create apertures that capitalize on the viscoelastic properties of clay. Okay, so to start off with grading light investigates how 3D clay printing can generate materially responsive engagements between ceramics and light. And so the research outputs of this project are essentially a series of stoneware and porcelain screens that vary in brightness and illumination based on how light can be obstructed, reflected, or transmitted across their surfaces. And the piece on the right is the piece downstairs as part of the beam exhibition. So this research develops a computational methodology for grading brightness and light scattering using toolpath tessellations. So in the building construction industry, we have this kind of preoccupation with regulating wall sections because this really streamlines the fabrication process and it regularizes material performance and reduces costs. And so these sentiments really kind of extend into the world of ceramic craft, which is also something we're very actively participating in. So the more consistent of a wall section you have, the more stable it will be during building, drying, and firing. But what 3DP with clay allows us to do is it allows us to grade complex sectional tessellations that's not really otherwise possible with other traditional methods of ceramic craft like slip casting, extrusion, throwing, et cetera, et cetera. So in this project, we're specifically working, and it's worth saying across all of our projects, we're looking at working with high-fired ceramics. And so we're working with 2 materials predominantly, opaque stonewares and translucent porcelains. So the stoneware you can see is obviously opaque, but it has kind of amazing plasticity and it's really easy to work with during 3D printing. The porcelain, however, is beautiful. It's translucent. It's got kind of this very pristine white color. It's able to transmit light, but it's those very properties that make it really great for working with light that also make it super difficult to work with because they essentially decrease workability. It's also noting that the porcelain is thixotropic, which means you have kind of a limited time of working with it once you kind of start material preparation. There's about a 36-hour window before the material starts to congeal. So it's interesting to note that these 2 prints were fabricated using the same essentially digital file and digital parameters, but you can see the 2 very wildly different outputs that are yielded with the 2 different types of clay. So as we just mentioned, these materials have really different behaviors when working throughout the stages of wet processing, drying, and firing the clay. But to kind of synthesize the work, the scope of grading light focuses on harnessing 2 types of 3D printed high-fired ceramic traits. And in the porcelain, what we're focusing on is light transmission through the clay body as a function of extrusion variability, and that really means variation in the wall thickness. And then in stoneware, we focus on the direction of incident light through porous multi-layered component sections. So when we're working with many forms of 3D printing, and specifically liquid deposition modeling with clay, the tool mark is kind of always a byproduct of the production process. So designers are working with this technology and addressing the tool path in a number of ways. So the first is it's just really a byproduct of form definition. Sometimes we don't acknowledge the tool path at all, but it's ever present. The second is the tool path as an expression of ornament. And then the third is the tool path as a function of material performance. And that can be anything from thermal performance, structural performance. In our case, we're really preoccupied with this mediation of light. And there can obviously be a lot of overlap between the three. But what we're really interested is in this third category of how the tool path manifests. So the grading light research is sort of categorized into kind of 4 light screen typologies. And they're kind of separated based on the scale of their apertures. So in these prints, how they work is the clay is basically directed into unsupported areas that creates kind of discontinuity and porosity in the wall section. And so to prevent structural collapse, you have to kind of isolate this plastic deformation and porosity and limit it to kind of specific moments within the wall section to make this work. And so this diagram on the screen, it displays the layer by layer deformation of each typology when mapped against the digital toolpath. So you can see the small typology has deformation that operates, at the scale of millimeters. The XL is happening over several centimeters. So it yields very, very different light scattering conditions. So in our research, toolpath design is really focused on modulating the behavior of light rather than conceiving of these sort of global geometries. So here, with the 3D print on the right, you can see kind of the high degree of plastic deformation that's taking place during the 3D printing process. And then on the left, what you're seeing is a 3D print kind of being recycled or reconstituted after structural collapse. So we're very occupied with making these things as large as we possibly can, despite the limitations of our tools and our materials. So this picture is a little bit deceiving. This thing is actually probably about 50 centimeters tall. So part of the exciting tension in the project is trying to make these things kind of as porous and as big as possible while avoiding structural collapse. So now we're just going to do like a really quick run through of the 4 different light screen typologies. So this is a small typology, and it's the only typology out of the 4 that's non-porous and works with the translucent porcelain. So the light is being mediated through the clay body. So brightness and light scattering in the small typology are primarily regulated by porcelain thickness, and it's achieved using 2 digital tooling operations. The first is extrusion variability, and the second is using the tool path to create these sort of waves that expand and contract in amplitude to change the distribution of material. So the diagram that you're looking at on the right is basically the digital tool path section, which is indicated by these sort of black dots. And that's overlaid onto basically the section of the physical print. And this sort of really was an effective tool in the research to help us understand the plastic deformation that's taking shape in the wall section. So this diagram, here we can see the relationship between wave amplitude and extrusion variability. So for the medium typology, in this typology, we utilize opaque porcelains and stonewares. And light is actually not passing through the clay body. What's happening here is this is kind of a multi-layered section. So light is actually kind of traveling through the wall section. It's not passing through the material. So the tool path in the medium typology is used to create a wall section that's essentially kind of split into 2 layers that you can see here. So there's kind of an interior skin and an exterior skin. And the interior skin kind of provides some structural stability, while the exterior skin is what's actually modulating the light. So what's happening here is as the kind of exterior layers pull away from that interior layer, that's what's creating porosity, and it's allowing more light to filter through at the expense of structural stability. So the amount of sag in each aperture has to be pretty carefully controlled in order to prevent structural collapse. So the image that you see here depicts a prototype actually being printed with a different type of clay body called earthenware, but using obviously the medium typology's printing parameters. So because earthenware doesn't really have the same plasticizers or the same viscid, meaning kind of sticky properties as the stoneware, it starts to delaminate. So it's kind of this very behavior that I was just explaining where the exterior skin is pulling from the interior.
So we'll move on to the large typology here. And the large typology is printed in stoneware and is kind of characterized by this directional illumination. So there's a large typology, it eliminates kind of glare by directing light downwards through these kind of channels that deform into like overlapping light scoops. It might be the easiest way to describe them. The depth of the light scoop is the thing that starts to grade illumination across these screens. Do we lose battery here? Maybe. There we go. So as with the other typologies, this diagram kind of displays that overlap of the physical print section and the print parameters there, or the toolpath section. The large typology might be the best kind of demonstration of this idea of the toolpath being designed with the intent of deformation into a sectional condition that can grade light. So the toolpath is not optimized, but the kind of reflection in the sag is. And we're always trying to kind of anticipate deformation with each iteration of this work. And there's so many factors that go into it, not just toolpath generation, but humidity, moisture control, saturation, print speed, anything down to like the temperature of the room at the time. Printing this in winter is different than printing it in summer. So it's a very kind of finicky process. The final kind of typology is the XL typology, extra large typology. And it's printed in stoneware, but it shares actually a lot of similarities with the small typology in that it utilizes extrusion variation as well as toolpath variation. So the extrusion variation allows kind of light to reflect off these shelves in the interior through these delaminated layers. As extrusion decreases up the piece, so does kind of this direct deformation. So, I have another one there.
Excellent.
So the apertures are designed to kind of deform heavily on the exterior and kind of remain stable on the interior. And these patterns kind of overlap to create two kind of like distinct light shelves in the exterior of the geometry, providing kind of this additional room for sag. The patterns realign on the interior to kind of form a more stable internal wall there. And the relationship between kind of aperture size and brightness in this one is nonlinear. It's too small of an aperture, you don't get enough light. Too big of an aperture, it collapses on itself, you don't get enough light either. So there's a sweet spot in the middle there that starts to grade light. So this kind of research, the prototypes we just showed you represent kind of a stage of a continuously evolving working methodology. And this is a photo from a recent exhibition at the Canadian Clay and Glass Gallery. And the oil lamp, what's on display here, it's also just on display there, are kind of the second generation of these light screens. And we're kind of working on the third generation right now. So grading light kind of allowed us to focus on toolpath design in the conjunction with kind of ceramic craft. It allowed us to tune material performance to light scattering effects at the scale of like a single print layer. And this kind of sits in contrast with the next project, which utilizes a lot of the same ideals, but on a much kind of different scale, which is Hive. So Hive is a masonry wall comprising of 175 3D printed clay units. And it was designed and developed by Ali Cho, Jim Shee, Megan Taylor, myself, Isabel Ochoa, and David Korea at the University of Waterloo. So Hive is a traditionally bonded masonry system. The stoneware units in Hive consist of kind of 4 interlocking hexagonal apertures. And the apertures have different degrees of opening and closing based on this kind of global geometry across the wall. So Hive kind of presented us an opportunity to access like kind of to assess the scalability and constructability of a lot of working methodologies we developed during grading light. And the final installation of this project is a privacy screen that sits at the Investment Management Corporation of Ontario's head branch. So if you go back 2 slides, Here. Here we kind of see like two masonry units, and they're like kind of at least in most kind of porous states. The installation was conceived as a traditionally bonded masonry system, adhered together with just mortar and grout. So the development of this project involved kind of working between digital and analog models to really assess the feasibility of this and get everybody on board that we can do this. We can create traditionally bonded masonry systems out of 3D printed ceramics. This is just an elevation that kind of illustrates that idea that each one in this kind of grid of 175 is unique, and it has a very unique place. And the whole thing spans 5.5 meters by 2.3 meters. So the commission was initially conceived of as 1,600 masonry units. It formed kind of single apertures. With this kind of this was very inefficient in terms of time and labor when addressing this idea of like a masonry unit as a kind of a 3D printed ceramic kind of fabrication process. So we worked with turning the original intent into a kind of a continuous print path that reduced this very large number of 1,600 units down to a scale that was more feasible, 175, while keeping this kind of same scale and same overall scale of the project. So in order to respond to kind of the dynamic material qualities of clay and formulating suitable mixtures for 3D printing at like such an extensive scale, there was extensive material testing, multiple kind of assemblies and mock-ups required to kind of prove that we could do this to both the kind of all parties involved, the architect, the client. There was lots of kind of convincing to go on that we could do this. And that was the kind of final proof of concept. So here's a shot of the edge condition that kind of fully illustrates that mortar bonded freestanding wall. And we worked very closely with masons throughout this project to kind of ensure that assembly was as simple as possible. So the last thing we want to touch on is just outputs with a visiting school program and the University of Waterloo School of Architecture. Most of these teaching opportunities have focused on developing masonry facade systems or masonry units because a lot of our funding comes from masonry conglomerates, and they're very preoccupied with this idea of the 3D printed masonry unit or aggregate systems. So student projects from the AAVS kind of, the whole thing was sponsored by Autodesk, and the workshop was supposed to be in person, but shifted to remote learning due to COVID. And as a result, we had to develop kind of a tool for simulating ceramic printing that the students could work on iteratively without kind of actually engaging with the material, which was very difficult. So the Autodesk team worked with us to produce this kind of clay simulator in Bifrost in preparation for this workshop that does kind of a pretty accurate job of describing kind of minute deformation between material layers. And that led to like many questions in this idea of like representation and simulation in the design and fabrication process. So we were able to kind of print all the final iterations of the students' work side by side with these kind of simulations that they did of their physical prints. This work kind of comes from an elective that we assist in teaching that's led by David Correa, material syntax. And we want to always kind of encourage students to find friction in material behavior and applications they find most interesting. So as a result, you have a wide variety of projects that engage with kind of design applications, and if you go to the next one here, to more structural capacities, which is always kind of fun to see. And we're really trying to engage this in a Canadian landscape, which is certainly much smaller than the landscape here. Yeah. So I think the final thing we'll leave you with is a small video, of just kind of some shots of Hive printing and the assembly of the Project Hive.
Thank you.
Any questions?
Thank you. Thank you for your presentation. Really nice work that you've been doing. The Autodesk model, the simulation model that you showed, can you slightly talk about these? Because it's simulating already the behavior of the liquid form getting shape, right? Yes. And from what I know, it's not a really easy process to model. Usually you use kind of, I don't know, we are trying, for instance, to use open foam, but simulating as a mesh. I don't know if you have any data about this or if you can
Yeah,
start about this?
Absolutely. So the models actually, it only functions at the level of simulating interactions between clay particles. So once you have kind of a moment of deformation and the particles in the model collide, that's when the model essentially stops. So that's really all it's capable of computing. So it's capable of computing sag and kind of mild deformation, but it's not going to simulate structural collapse for you.
Okay.
So it's not a way of testing structural failure.
It's, yeah, they've got, Autodesk has got like a great basis for fluid simulation and other simulation, particle simulation. Clay is none of those. It's like straight down the middle, so it's very difficult to kind of, so the best way I can describe that kind of model is, it's almost like it's not based in any of those simulations that they already have basis for. It's based on something completely different. And the best way I can describe it is almost like a sticky rope that kind of has a kind of a degree of deformation that, yeah, engages with a certain kind of layer of deformation. It has the capacity to kind of generate full structural kind of collapse, but in doing so, it's just we found that the computational tool became actually heavier than just working iteratively through material processes. Like that computational tool at a certain point becomes so heavy that it's taking hours to simulate these really kind of complex deformations, and at a certain point you can fire up the printer and print it in 30 minutes and get a lot more kind of feedback. So we decided to kind of, we made that decision to limit it to something that students could get a feedback that generates, so it generates kind of aesthetic deformation in seconds because of that.
Thank you. Just a small question about here, wall. How difficult it was to work with difference in tolerance on blocks?
Quite difficult. So there's a lot of tolerance you can see embedded in the joints. So the joints are quite large compared to a traditional bonded masonry system. So we kind of had to build that in to the tolerances of the whole thing. But you know, the final wall was put together by a professional team of masons. The thing that we created in our studio, we sort of laid every brick lovingly, but you know, there's only so much you can do when you're not an expert in the trade. So yeah, to answer your question, there's quite a lot of tolerance built in.
Do you know how much the wall growth after it was assembled?
Oh,
There's actually, we through extensive like testing, we had a sneaking suspicion that this would be the final, so it's actually pretty accurate to,
Okay.
I don't think there's like much growth in the final iteration there, but yeah. I think the masons were like, we gave them those tolerances, we gave them quite large tolerances. I think they could have pushed it, they could have brought those numbers down, but I think we were better like safe than sorry. We had already kind of like scaled it to a certain kind of mortar joint, and they were happy to do that, so.
Thank you.